the way I want to structure this is just first of all to talk about how to learn satellite image interpretation. This is not something that we can, dive very deep into in an hour or two. This is something that you learn for years and years. Then we want to talk a bit about the optical spectrum, just to remind ourselves about how optical or electromagnetic radiation works, which bands we have, how individual satellites are placed along the electromagnetic spectrum. Then we will talk about different processing levels for Sentinel data. I think this is going to be familiar already, but it's nice to remind ourselves. And then we are going to look into different images of vegetation, images of urban scenes, snow and ice, and deserts and arid regions and fire. And then we will have a bit of a summary. I'm going to show images. The links in the browser are in the chat. I'm not going to pull them up in the browser right now because that would be a bit cumbersome, but I will talk specifically about different ways of visualizing the same images. So sometimes we will look at various processing levels. Sometimes we will look at various scripts or palettes to look at the same thing. Okay, so, well, how do you learn satellite image interpretation? What you actually want to do is collect information that you can compare with your satellite image. So if you start thinking with this mind, a lot of the information, a lot of the spatial information out there is something that you can compare. The simplest one is aerial imagery. So you can use Google Maps. And then if you're looking at the satellite image, you pull up the same place in Google Maps. It's not going to be at the same time. Often you don't exactly know the date of the image in Google Maps, but it has high resolution and it helps you understand, what the structures are that you see and what the changes are. Sometimes we even go into Street View. I've actually used Street View a lot for crops. So when I'm not sure about a specific crop where I have a weird land cover class, I can go into Street View, and sometimes I find that it's, I don't know, an energy forest plantation, which I've never seen before, or a small wetland. At least within Hungary, of course, not all countries have Street View, but it's a nice way to sort of virtually be there in place. Field photos, always a good thing. So if you can have photographs of your own field work or somebody in the field, or I don't know, landscape photographs of somebody's outdoor trip, it's always nice to compare them with satellite imagery. Geolocated and chronolocated videos. Again, you check a video on YouTube about the landslide or a geyser eruption, and if you know the place and the time exactly, then you can compare it to a satellite image and even verify it. And sometimes even online news. So stories about natural disasters or war or just major building projects are something that you can always follow up, and then you will have a bit of a grasp. So try to practice regularly if you really want to get a hand in image interpretation. The approach I like to encourage is to find a favorite spot and to look at every single Sentinel-2 image that comes in. Make it a habit of checking once a week or something the images, and then you will really be able to follow what's going on. This is a place not very far from where I live. This is a mountain called Pilish, so it has sort of a shape like this, and we're looking through the seasons. So this is a time lapse, as you know, every single cloud-free or more or less cloud-free image, and then you can see how the seasons develop, and a lot of the effect of the topography is there. Like sometimes you have snow on top of the mountain and no snow at the bottom, or the autumn colors come in differently with the elevation. So again, one of these images is nice, but as soon as you start comparing a time series, then it's going to tell you a story. So it's really worth it. A nice functionality for this is the pins in the browser. Again, we haven't explored this, but it's really easy to add a place to pins. It's the same as, add to compare, and then beside that you have add to pins, and it gives you a pin library, which is assigned to your user. And so you can go back to the same places again and again. There are some really good satellite image artists on social media who are worth following because they have like crazy beautiful images from lovely places. And I want to encourage everybody to keep looking at the Copernicus Data Space Ecosystem Gallery, because we are really trying to provide a curated collection of images. And it always has an explanation both about the sensor or the visualization process and what you see. Oh yeah, online news. Let me give you a story. It's COVID. I'm sitting at home, locked up, and there's this news that somebody has stored 100 or so yellow buses on a side road somewhere in Western Hungary. And so, is it for real at all? Or is it fake news? Is it just an advertisement for the bus company? is it possible to take a look and see these buses on satellite imagery? And then again, our 10-meter pixel comes in. So do you see a bus on a 10-meter pixel? Well,
one maybe up or what's 100?
yeah, that's the thing. That's the thing. So the news feature, it had a date, the 23rd of April. Oh, it's not 2023, it's 2020 probably. And yes, it's visible. Here are the buses, right? So these are the things, you hear something weird or something fun, go and take a look. It's just a couple of minutes and you will come out with a lot of experience. So these are the buses, and if they are very bright yellow and if the conditions are right, then you see them. Again, finding, yep.
May I add one little thing? Yes, here you see a bus on a 10 meters pixel. This is something that is not you to compare only the pixel size to the size of the bus, but also how dominant the reflection from the bus it is. Because when you are integrating the energy from a pixel, and there is a very strong source in that pixel, it will jump up. And that's why you can see roads which are only 6 meters broad. You can still see them on the 10 meters resolution images, because there is a big contrast between the road, the spectral signature, and the side spectral signature. Sorry for it.
No, that's totally relevant. Yes, please.
More story about this kind of thing. I had a friend and she was on the train. She was texting me, "Hey, I'm seeing human bones on the window. Like I'm going with the train, I'm seeing a lot of human bones." I was like, "What is happening?" And she's like, "I don't know. It's just some more digging and a lot of human bones." And then she said, "Go look on the satellite images." And I was like searching to find something about. There was nothing on the news. And I was trying to look exactly on this Sentinel-2 imaging, and I seen the diggings, but I couldn't exactly see the bones, even though there are a lot of them. And then I found out on the news, it was I think one of the biggest archaeological sites discovered in Romania, because they were waiting for a new train line, and they found this a lot of human bones, and I do not love this.
Yeah, nice. Yes, pixel crosstalk. We've talked about that. So finding a favorite spot. I was lucky because I used to live in this place, Tirang Peninsula, and I was even more lucky because I made a habit of going for a walk every morning for a while. It was a bit of a personal thing. I would send my children off to school at 8 o'clock. I would start work at 9 o'clock, and during that time, I would have time to explore the peninsula. And this means I had for that period a really, really good understanding of what is where. And then if you get a satellite image, like this one was actually posted by Copernicus EU, then there are just so many pieces of information that you can locate. This is an artificial football field, actually, the dark spot there. I haven't been able to recreate this composite. I don't know the script for it, unfortunately. It's beautiful. It has to involve sort of shortwave infrared in some way because the football field is so dark. But there's all these different features, like a rock patch in the middle of the lake. If you regularly visit that lake, you're going to see it. So these are the things that's common to advantage when you have a place where you are outdoors a lot. This is the electromagnetic spectrum. So it goes all the way from wavelength of 10 to the power of 3 meters down to 10 to the power of minus 12. And these are the structures that would sort of interact with it. So where is Sentinel-1? Which of these guys here interact with it? Microwaves? Yes. 10 to the power of minus 2. A couple of centimeters. Exactly. Butterflies. So that's the sort of sizers. Oh yeah. Well, I had the answer there for you. And then Sentinel-2 is somewhere between visible and infrared. And actually Sentinel-5P has some bands in the ultraviolet range. The atmosphere is not transparent for the ultraviolet range. That's why we are using it to monitor the atmosphere, right? Because various gases have a strong signal in ultraviolet, including ozone. And so that's why Sentinel-5P works here. And these things here are called atmospheric windows. So parts of the spectrum where the atmosphere is transparent, where air is transparent. And for other parts of the spectrum, air is not transparent. Like for parts of infrared, it's semi-transparent. That's why we have the greenhouse effect, global warming with CO2. So this all sort of adds up. Oh yeah, and on the other side you have frequency, but I mean, radar scientists often talk frequency, and optical scientists, they talk nanometers. So this is sort of how the electromagnetic spectrum works. Or to take it with another approach, we're going to have a series of these graphics where these colors represent different kinds of radiation. So with orange being microwave, this pink being shortwave infrared, purple being near infrared, gray visible, red and green. So these are all different parts of visible light and electromagnetic radiation in general. It's always good to remember that visible light goes from 700 to from 400 to 700 nanometers. So clouds, they reflect pretty much everything except microwave radiation. Something that's very hot is emitting a lot of shortwave infrared radiation, and vegetation will reflect in the red and the green. So if we separate the Sentinel-2 image into its optical bands over a normal place with vegetation, we are going to see different intensities. Remember the curve in the spectral explorer, like really low in optical or in true color, and then it goes up in the infrared and sort of gradually down. This is what we see, right? Quite dark in bands 2, 3, 4. Band 1 is also a blue band that we use for radiometric calibration, for cloud mascades. So this is the band we use for clouds. And then at the red edge, band 5, 6, 7, it sort of goes up. Band 8 is the broadband infrared. 8A is a narrowband infrared, and then it goes a bit down for the shortwave infrareds. So this is the typical response of Sentinel-2. These are just the band centers. And no, the band minimums and maximums. So some of the bands you will see are quite wide, like B8, 832, 853. No, that's not that wide. Okay, then it's the band centers for the individual satellites. So yeah, because it's a tiny bit different from Sentinel-2A and Sentinel-2B, which turns out after you build the sensor and then you calibrate it. Just nice to know. Okay. Once more, this is how we create a true color image. So a normal image that you see on your computer screen is composed of red greens and blues. This means that we are assigning some of the band values to the red, green, and blue channel, or if we are working with a single number, then we are assigning it to a color palette, like we did for NDVI between light green and dark green. Different colors are, of course, different products of red, green, and blue being mixed. This is, again, something that's not so easy to comprehend, right? If I have a yellow image, how much red and how much green do I have? Actually, quite a lot. If I have something like this bluish grayish, how much of each band does it use? Sometimes you can use this as a bit of a cheat sheet when you're trying to understand 3 different parameters assigned to red, green, and blue. But in general, I think we often get colors like yellow or purple where we need to understand just the way they are mixed together. Yes, and then we have the near-infrared false color composite, where we are assigning one of the near channels to the red and the red to the green, and then we're getting a different set of colors. We've explored that already in the browser. And coming back to the spectral signature of vegetation, we are going from 0.4 micrometers, so 400 nanometers all the way to 2,500 nanometers. And these are the typical spectral signatures. And look, reflectance goes from 0 to 0.5 here. So we don't really have anything in the natural world which reflects close to 100%. If it does, then it's probably specular reflection or an artificial surface or both. Specular reflection, everybody knows what that is? Sort of, okay, let me explain. So normally, if we have a surface which is slightly rough, then it's going to reflect light in every direction. That's why we see things, with our eyes, because some of the light is reflected back to our eyes. We have Lambert's law, which explains that the amount of radiation is typically proportional to the cosine of the incidence angle of light. And this is a relatively simple law, which is actually quite a good model of normal reflectivity. And then sometimes we have extremely smooth surfaces, which are not reflecting light in all directions, according to Lambert's law, but they reflect light only in the same angle as the light is coming in, like a mirror. You know, you can shine a light from one end of the room to the other with the mirror. And some surfaces are like this: water, glass, sometimes metal roofs. And then either they are facing away from the sensor, and then it's very dark, you don't get any reflected light, or it's facing towards the sensor, and then you get an extreme amount of reflected light, like a flare. So this is what specular reflection looks like. So that's why, I mean, under normal Lambertian conditions, we are expecting reflectance to go all the way up to 0.5, 0.6, or not much more. This is the typical spectrum of vegetation. This is the red edge. And then depending on the type of vegetation, the type of plants, these peaks are going to be slightly different. And if the vegetation is dry, then the red edge is a lot flatter. You see it's a lot less steep. Or if the vegetation is stressed as well, then this curve changes. And so this is our basic way of discriminating individual classes. Okay, now we have a vegetation index, NDVI. We all know the formula, how it works. Again, it's comparing this over here, the red, to this, the near infrared. That's what NDVI does. And so we typically assign it to a green palette. You can visualize it with grayscale, or if it's, of course, a lot more intuitive if you use just the green palette. Okay, now we have a bit of a different situation. Imagine a forest fire and some clouds. So normally clouds would reflect everything from both red, near infrared, and shortwave infrared. But shortwave infrared is not really obscured by smoke. So this is the fire here. We don't see too much of a signal on the red or the near infrared, but a very, very strong signal in shortwave infrared. And for vegetation absorbs shortwave infrared, or it doesn't reflect that strongly. And so there's no very strong signal here. The strongest signal is in the near infrared, if there's no cloud. We're going to explore these scripts a bit to try and wise by visualizations and to identify them up there. Okay, now optical spectrum. Questions to the optical spectrum?
Oh, but
Comments, yeah?
in that will, let's see, some because it's K and V R, K again.
Yes, K and NDVI.
So is it today? I don't know.
Yes, we're going to look at the custom script that I can actually explain here. So this is the regular NDVI formula. So the difference between near infrared and red is then divided by the sum. And this is something that we linearly assume that it correlates like with a very straight linear correlation to the chlorophyll content. Because dry vegetation is like this and green vegetation is like that. So it's not a very bad assumption to assume that this is linear. And kernel NDVI is changing this transfer function. It's saying that it correlates, yes it does, but not in a linear way, but in a sigmoid way with a tangents hyperbolicus function. But that function is a bit sensitive, so you have to also take the square of this and then the square root. So this is that's why KNDVI is a bit more complex. But for optical interpretation, it's like a contrast stretch. So it applies a bit of a stretch to the intermediate range of NDVI, where most of the signal is. And it also smooths away the tops and the bottoms a bit so that it doesn't saturate. Because again, with NDVI, you see a lot this kind of thing, right? Big green patches, because for high biomass, NDVI is saturating. But KNDVI is not saturating. So that's actually a very, very nice tool for visualization. There's also a paper where they compare it with NDVI for classification or for yield monitoring. And they say that it's actually performing better because of the scaling thing. That's actually going to come down to the machine learning algorithm that you use, because some machine learning algorithms are not sensitive to scale anyway. Like random forest is not, because it does its own scaling. So in those cases, it's not going to make a difference. But especially for visualization and like more linear regressions, it's a really, really nice tool. I think it's like the next NDVI.
Yeah, that will be my second question. Thank you very much for the modeling.
Yes. There's a paper by Gustav Kampwall. I'm not quite sure how to pronounce his name, because he released this concept of KNDVI. I think he published it in Science, actually. A unified index of the terrestrial biosphere. That's the title. Not that difficult to find. So that would be the recommended reading on that one. Okay, So remote sensing is a mess. I've once been to a remote sensing summer school in Finland. And so after courses, we were sitting in the sauna and everything was like all misty and hazy. And so Wolfgang Wagner from TU Wien, he said like, this is what remote sensing is like. So trying to read somebody else's newspaper across the sauna, because there are so many different things interfering with the optical signal, right? So what you get is a combination of multiple factors, many different products. First of all, sunlight, right? The amount of sunlight that you get is going to very heavily influence the signal that you get back. This is a passive sensing process. So we have a lot higher reflected intensities in summer, or where the incidence angles are high. And also we have sun shadows depending on the season. So this is going to be one of the first things influencing our image. Then we have the atmosphere. Again, clouds, cloud shadows, haze, smoke, smog. These are all things that are going to influence our signal. And we're not down to the terrestrial surface either yet. The surface structure is going to influence the signal. Terrain topography. Again, because of the Lambertian law, the incidence angle of our sensor to the surface is going to influence the amount of energy we get back. It's not completely independent. With radar satellites, the slope is a very big modification factor because we are looking from the side. And then some slopes will reflect it very strongly and others very weakly. But also with optical imaging, slopes will have a bit of an effect on the amount of energy that's reflected back. Land cover and vegetation is very flexible. It changes its color, it changes its optical properties depending on its physiological state, depending on what the plant is doing. And then we sometimes have sensor artifacts like RGB movement streaks or these specular reflection flares, what we call them, very, very strong reflected signals. Have you seen an airplane on the Sentinel-2 image? Okay, we'll go back to this after the talk part and I can show it. Airplanes are typically split up into a red airplane, a green airplane, and a blue airplane. Okay, let me show this. Yes, this is what we want to see. Right? So the artifact is that we see the same airplane 3 or 4 times. And this is because the optical sensor of Sentinel-2 is built in a way that the filters are not running at the same time. So the individual bands are actually sampled like half a second later in a sequence. And that means that if something is moving very fast and it's close to the sensor, then it's creating this movement artifact. And so this is, again, something to keep in mind when you're looking at something that's very fast. I'd even seen such a movement artifact on a ship once. That was a very fast ship. So this is the type of thing that the characteristics of the sensor are influencing, and then you have to keep it in mind when you're looking at an image. Okay, let me go back to my slides. Okay, off we go again. So this is an example, right? This is a near-infrared false color image of meanders and sort of snowy conditions just north of the Lake Tisza Reservoir in northeastern Hungary. And so again, what you see is a combination of the atmosphere and the surface conditions. And so, for example, the effect of topography is really quite strong in this image. It's partly emphasized by the snow because the snow is packed along the snowbanks. But these little stripes that you see up here are actually like very, very small changes in elevation, but they stand out because of the low sun angle and because of the snowy conditions. And again, you see these fish ponds are frozen over. The vegetation is in a winter state, so it does give some sort of near-infrared signal, but not very strong. There's some haze probably over this part of the image, and this is also more snowy. And so if you have an image, then you have to keep in mind that these things are also part of what you observe. Let me give you another example. Is this on the ground or in the air? In the air, yes. That's in the air. This is northern Iceland, and rivers in Iceland have very strong seasonality because there's snow cover, and so in spring the snow melts. Sometimes it's also related to volcanic processes. And so they have a very large discharge over the spring and summer season, moving a lot of water, moving a lot of sediment. And then in autumn, when they are moving less water, but the winds are already coming and the snow is not yet there, a lot of the dust is just picked up and moved into the atmosphere. So these things will also influence what you see. A couple of years ago, I think it was 2022, we had a period in spring of very, very intensive haze from Saharan dust. And the satellite images were useless for a couple of weeks all over Europe. The atmospheric correction was all over the place. The colors were really, really weird. And so you had to keep it in mind. What I'm seeing is not the ground, it's the dust in the atmosphere. So this is a very important influencing factor. Let's go to the mountains. This is the Sentinel-2 level 2A image. This is Treitzinnen in the Dolomites. And what you see, I'd introduced before this algorithm, which is trying to even out the effect of the slope and the topographic shadows. And you see that it's really, really struggling because the slopes are so intensive, right? So we have this shadow here, which is the shadow of the mountain ridge. And then these white blurs are the level 2 algorithm trying to correct them. It's estimating the shape of the shadows based on the topography. Actually, it's not doing a very bad job, right? This is a pretty good guess of that. Yes. For forests, sometimes you have to use the level 2 image, and if the slopes are not bad, then the correction is okay. But in a really, really rugged place like this, you have to keep in mind that the level 2A correction is all over the place. Yes?
Can you please explain a little bit the level 2, what it means? Or shall I give a few words which I wanted?
Yes, please join in on that, but come over here so that you're in front of the camera and the online people see you as well.
So those who followed courses with me already heard about atmospheric correction and heard about top of the atmosphere reflectance and ground or bottom of the atmosphere reflectance. And please remember the level 2 preprocessing is resulting in a ground reflectance data. The idea is that all distortions which are there because of the atmosphere, because of geometry, because of the topography, should disappear, and it should be a kind of orthogonal projection, and that reflectance that you measure at the ground. Therefore, what you see here, it shows that there are limitations of that. And that's what András is talking about. But please remember that the level 2 data is the data that if you want to compare time series, you have to use. Because the time series, the reflectance is that physical property of the surface that is the same, that remains stable throughout the time series. Of course, not all level 2 corrections are resulting in 100% good result. Therefore, when you are looking at the time series of, for example, an NDVI calculated from level 2 data, then you will see sometimes minor fluctuations in your data. So this is something that we are talking a lot about level 1B or level 1C correction that is containing still atmospheric effects. And the level 2A has removed atmospheric effects. Sorry for
That's perfect. Thank you. Actually, let me go back quickly to NDVI because there's a reason why we are using it. If you are dividing by the sum of near infrared plus red, then that means that you're equalizing out a lot of the noise that's coming from difference between individual images or noise in the atmosphere, things like this. This is why it's such a robust index, because it's a product of the individual bands that you are using right there. So since it's not just, we could be using just the near infrared intensity, right? That would be a signal of how much vegetation we have. But since we are dividing by the sum of the two bands as well, it's a lot more robust to atmospheric distortions and all the processes that you get through the level 2 correction.
But still use it from level 2. Yes, of course, possible. So this robustness works with the level 1 images, but they are not comparable then to each other.
That's right. That's right. Okay, so this is the same thing with level 1C data. You see all these massive big shadows. Probably if you would want to explore what you have in these places, you could either use the advanced options tools and just improve the gain or the contrast of the image, or you could use a highlight optimized natural color, because then it's going to stretch your dark and bright places. You're not getting oversaturation of the sensor in very bright places, and you're not getting the dark places as dark as they are. Now, what happens if we look at level 3 data? So the monthly mosaic, is it going to be better or worse? Is it better? It's a product of level 2 images. It's built from a series of level 2 images. So that means that the whole shadow correction and slope correction artifact is there. The clouds are filtered away, which is okay. But still, a lot of these correction artifacts, I mean, look at this place, right? Why is it white? Is this snow? No, it's not snow. It's just the overcorrection from the slope. So in this specific case, you would actually probably want to create a mosaic from level 1 data. But even that's going to be messy because the shadows are changing their direction. You know, see on some of the images, the shadow is here. On others, it's there. So it's very difficult to create a good mosaic from a place like this. Again, if you're investigating mountains, if you're into snow or avalanches, then you will always have to keep in mind that you're looking at very steep slopes. And so the level 2 is struggling. One more look at vegetation. This is where the quarterly mosaic actually comes really in handy. So a typical image, a typical single image of this place. Oh wait, no. Yeah, for some reason I'd lost the individual Sentinel-2 acquisition of this place, but normally this would be extremely cloudy. The clouds are patchy because that's what tropical rain clouds are like. So it's possible to create a high quality mosaic from them, filtering away the clouds individually and summing up the bands in between. And as you see, you can really sort of follow through the structure of the vegetation or the ecotone between the city and the rainforest in places like this. This is what an intact or more or less intact rainforest is going to look like. And these are the kinds of traces, the roads and the sort of deforestation marks that you are looking for when you are investigating deforestation in tropical forests. Savanna vegetation is characterized by very high seasonality. So what we see, of course, again, a lot of clouds, super difficult to create a decent mosaic, but there's a rainy season and a dry season. And so the green and the dry part are going to be very, very different. Again, a lot of this is exploited in weird ways in the news. Did the news story about the Victoria Falls drying up reach you? I should have brought an image. Again, I'm an ecologist, so I'm on email list of people who are concerned about the environment a lot. And then somebody posts a news item, Victoria Falls has dried up, it's the end of the world. And I actually went back and took a look at the satellite image, and there is barely any water in Victoria Falls. And then I just looked at the other season. Okay, let's see, what does it look like 6 months away? Is it seasonal at all? And of course, yes, in the rainy season, it's big. And so I went back through Sentinel-2 images and then through Landsat images all the way to the 1990s, and it turns out that it was pretty much the normal seasonality of Victoria Falls. So even though it was a drought year, it was a specifically quite dry year in that location. But the waterfall did not look very different from what it would normally look like in the dry season. So I actually wrote back to those guys, look at the evidence before you're so concerned. Still, the drought in Africa is a big issue, and specifically that year was very bad. But you can disprove something like this if you have the right images. Agriculture. We've seen a lot of agriculture seasonality, but this is a very strong signal that you see a lot in Europe. Do you know what this yellow thing is? Pardon?
So it has been dried. It's like harvesting time.
No. The image is from late April, if that helps. Sowing. No. This is the flowering of oilseed rape.
Yeah.
Yes, so it's one of the largest crops grown in Europe, and it is a very, very characteristic signal when it is flowering. It's also quite nice outside in the field, but it has a very strong yellow signal, which can even be picked up with a spectral index. And then if you are looking at crops and trying to categorize them, oilseed rape is very easy to find because of this yellow signal. But it's across large areas, and you have to know what it is because it has this really, really weird color. So much for my vegetation examples, and we can look them up later. Urban areas, again, shadows come into play here, right? This is a level 2 image, but the level 2 correction is done based on the terrain model, not on the surface model. So buildings are not taken into account there. And the image is from late November. So all these tall buildings are pretty massive, big shadows, which is actually nice because it helps you understand the structure of the city. So if you are trying to investigate an unknown city, or if you want to create a nice image of a city, then taking a time slot where the incidence angle is very, very low, the sun angle is low, is actually helping you, because then you can see the signal of all these big buildings. And it's actually nice if you create the time series throughout the year, because the direction of the shadow will change according to the season, like a big sundial. So this is also a fun thing to explore. For cities, this is Hyde Park, by the way. For cities, true color is often the best thing you can use, unless you are into specific things like radiation hotspots or urban green space. I think that many different urban development things can be nicely explored just using a true color image. This is another true color example. This is Sao Paulo in Brazil. This is something like 60 kilometers across. What you see here is the large amount of like low buildings packed very densely together, informal settlements, favelas. So this is again one of the applications of remote sensing, because these are not mapped on official city maps. They change very rapidly as people migrate or move. And so we are trying to use these to follow up the movements of the population, because you don't have a population census. The only thing you have is this. So this is one way of using Earth observation. Glaciers, cryosphere. The big problem if we are looking at snow is always oversaturation. So in this place, you barely see any texture. And then this is the main application of highlight optimized natural color. So this is where you really want that contrast stretching for the dark and the bright places to show you the topography or the snow patterns in these areas. Of course, satellite images are used a lot for tracking changing glaciers and changes in the cryosphere, snowpacks, avalanche risk, and that uses snow indices. So the normalized difference snow index is one of them that you have in the browser anyway. But this is just the typical signature you see. Very often, snow stays longer in valleys or in shadowy places, so we will see quite intricate patterns as the snow is melting. But this is the typical image. Actually, specifically for snow, if you're interested in more, we have a really nice webinar by a mountain guide called Michael Engel in the CDSE YouTube channel on how to interpret different kinds of snow. So that's a fun thing to watch. Now this has a really weird way of contrast stretching. It's called nonlinear dimming, when you're looking at the differences between the individual bands, and then you're adding that to the red, green, blue channel. Again, in normal true color, the whole area would be completely white. Maybe you would see some shadows, but by applying a relatively complex script, which looks at these differences between the bands, you get this bluish tint and an extremely detailed view of the patterns in the snow. This is a place in Antarctica, Reeves Glacier. So the link is in the chat again. You can look it up, and then you can also look at the visualization algorithm. We're going to shift over to deserts in a second. Okay, deserts. The lovely thing with deserts is that there's no vegetation, so you actually see the lithology, the rocks. And so very often, again, a simple true color image is already giving you an impression. You won't be able to identify which rock is which, but you will see the differences between them. You will be able to separate it into different lithological units, unless you've got sand. So this is a place in Morocco with what you call star dunes. They form when the wind is blowing regularly from many different directions. And so this is like a bare rock surface. It's a depression filled with sand, and the sand also moves around a lot depending on the wind. This is what it would look like. Again, if you want to look into the topography, an image with a low sunlight angle is helping a lot. So this is again a late winter image of Glen Canyon National Park, where you have all these slopes highlighted by the shadows. And shortwave infrared is actually also quite handy for geology. So if you have no vegetation, then if you look at this rainbow of colors, this is the shortwave infrared composite, where different clay minerals have different optical properties, and you can separate individual units of them. Or also over here, in a true color, this place wouldn't look particularly different from the rocks around it, but it has a very different signature in shortwave infrared. So we use that for geology or natural resource prospection as well. We're coming close to the end. This is the wildfire. So this is what a fire looks like on a normal true color image. You see the source smoke, and it sort of covers everything. Shortwave infrared composite. Remember that the shortwave bands are sensitive to heat. So you would already see the warm places. But then there's actually a really nice visualization where a small decision tree or a small spectral index is applied, and the places where the shortwave infrared is high are assigned to the red channel. And so you get a strong red signal, and everything else is true color. And so this is the visualization that you use for forest fires. We're going to look at it in the custom scripts section in a bit. So this was my little introduction to Sentinel-2 image interpretation. You see that it's a very big and very complex topic with many different applications. Take a look, keep viewing images, and sometimes you will find a piece of treasure or a gem like this. This is one of my favorite pictures. We are on Lake Balaton. This is a harbor where there's a river running into the lake. It has very black water because it's coming through the wetland. And what you see here is a von Karman vortex street, with these whirlpools going left and right at the scale of a couple of kilometers funneling out from the harbor.